Welcome to Chapter 2, the Binomial Expansion. This is from Pure Mathematics Year 2. And today we're going to look at how to expand 1 plus x to the power n. And this is a continuation or an extension of the binomial expansion that you learnt back in Year 1. I've put the definition down here for all of this, all of the material that we're going to cover today. You don't need to worry about remembering these. These are given to you in the formula booklet. All right, we're just going to extend it. And we're also given the, or you're also given the definition of a combination. And we're going to use this extensively throughout the lesson. Now, what I would like you to do first is we're going to have a look at the warm-up questions. So if you'd like to pause the video and have a go at the 4 questions that are on the board, okay, and then when you've done that, just unpause the video and then we'll go through the solutions. All right, so let's have a look at question 1. So you're asked to consider the statement n and then lots of other factors equals 0. So we have an expression on the left-hand side is equal to 0. And we're given this matrix of values here. And we have to assess which of these values would make this a false statement. And it says value or values. So there could be one or there could be more than one. We don't actually know at this stage. All right, let's consider it case by case. Now then, we want to make this a false statement. Now, as you know, if you multiply numbers together, it doesn't matter what they are. Okay, and then you know that the answer must be 0, then you are forced to consider that the only way that could happen is if one of those numbers was 0. Okay, but you could also have, for instance, 0 multiplied by 0 is equal to 0. Okay, so at least one of the values on the left-hand side has to be 0 for this to be true. Now let's test them. So if we test negative 0.5 here, well, which of those brackets in front of us is going to create 0, if any? Well, I can see that if I sub negative 0.5 into 2n plus 1, that's going to create 0. So that means that we can disregard this. We don't want to create 0 because that would make the statement true. We're trying to make the statement false. Next up, let's have a look at 0. Now, is there anywhere where I could sub in 0 itself to create an equation that actually is true? 0 equals 0. Well, yes, I could put 0 in over here, which means that this is also a true statement, which I need to disregard. All right, so we're going to cross out that one. Next, let's try minus 2. Now, do any of those brackets create 0? Well, yes. I think this one, if I put negative 2 plus 2, that gives me 0. Okay, so we can disregard that. Now we're on to number 1. We're going to the bottom left. Well, if I put number 1 into this bracket here, that creates 0, so we can disregard that one. What about negative 1? Now, we've tried 3 of them. One candidate could be this one here. But if I square negative 1, of course, I'm going to get positive 1. Minus 1 times minus 1 is 1, and then I add 1, I get 2. So this one is not going to generate 0 in any of these factors. Okay, they're just numbers. All right, they're just expressed algebraically. So this one actually does work. It's going to give me a false statement. Okay, so negative 1 is not a solution to that equation. And then if we try 0.5, well, the only one we haven't tried is n subtract 2 here, and clearly that's not going to create 0. If I put 0.5 subtract 2, I get negative 1.5. So this one is also going to give me a false statement. So that's part A. And then in part B, we are told, is the following statement sometimes true, always true, or never true? And the statement is, the square of a number is always greater than the number itself. Well, when you have a question like this, it's always an advantage to consider the sometimes true scenario. So in other words, can we think of counter examples? I mean, we can think of plenty of examples where it is true. I mean, that's what it's driving at. I could very easily just say, well, 2 squared is 4. And we know that 4 is greater than 2. So that works. Okay, it definitely works for all the positive integers. But is there a situation where it's not true? Well, it just says a number, okay? Any number we choose. Now, an obvious one to pick would be 1. 1 squared equals 1. And we know that 1, well, it's not greater than 1, is it? Okay, so it wouldn't work in the case of the number 1. Another one we could try would be a fraction such as 1/2. So if I do a half squared, we get a quarter. And a quarter is less than a half. So we actually get all 3 scenarios. We can get numbers that are greater than the number itself, equal to the number itself, or less than. Okay, and another one that would be equal, of course, would be 0. 0 squared equals 0, which are both identical. So this is sometimes true. So we'll just fill it in. Sometimes true, and then we've just provided several pieces of evidence to back up our claim. Okay, so you'd have to provide some kind of counter examples where it doesn't work. So it doesn't work for fractions between 0 and 1, or negative fractions for that matter between 0 and -1. It doesn't work for 1. It doesn't work for 0, but it does work for the natural numbers. In fact, all the positive real numbers greater than 1. Okay, and less than -1. So that's question 1. Now, question 2, I'm just going to create a bit of space here. Question 2, we're asked to expand some brackets. Now, if we do this explicitly, I just want to make a point here about what you're actually being asked to do, and just to stop you making silly mistakes, really. If we're asked to expand 2x to the power 3, I'll write it out explicitly. Please remember, it's 2x. Oh, I've got eraser again. 2x multiplied by 2x multiplied by 2x. 2x to the power 3. All right, so let's have a look at the coefficients of x. So we've got 2, 2, and 2, all multiplied together. All right, well, that's going to give us 8. So let's write that in. Okay, and then we have x multiplied by x multiplied by x. So it's obviously going to be x cubed, like so. So no problems there. And obviously the shorthand way is, you can see directly, it's going to be 2 cubed, isn't it? So 2 to the power 3. 2 to the power 3, it's given to you, so that's 8. And then x to the power 3 is x cubed. Nothing more to say on that, really. So let's have a look at the next one. Now, we have to expand 1 plus x to the power 4. So we're leading into the main body of the lesson here. This is what we're going to be looking at today. Now, there's several ways you can do this. You could expand it explicitly by multiplying all the brackets together, which would be a lot of work. You could use the binomial expansion, which is given to you in the definitions. Or you could even use Pascal's triangle, which is the same as using the binomial expansion. So I'm going to use Pascal's triangle for this, just as a reminder, because this will give us all the combination coefficients. But before I do that, I think I will actually write it out using the binomial expansion. So if I want to expand 1 plus x to the power 4, well, using the definition, it's going to be 1 to the power 4 plus 4, choose 1. And then remember the 1, which is the first term in the expression here, it drops by a power. Okay, so it's going to be 1 to the power 3. And then we're going to bring in the x. So we're now going to have x to the power 1. All right, and then continuing on, so we're going to have plus 4, choose 2, 1 squared. Again, the 1 drops by a power. And then we're going to have x squared. Something else to notice here as well, the powers should always sum to your n value, which is the 4. Okay, they should always sum to 4. All right, that's how you know you're doing it correctly. All right, let's continue. So that's going to be, oops, use the highlighter there for that one. Let me just erase that. I was getting used to this zoom. So plus 4, choose 3, 1 to the power 1, and then it's going to be just x to the power 3. And then I'm just running out of room here a little bit. Plus 4, choose 4. Or in fact, we don't even need to put 4, choose 4, do we? Four choose 4 is 1, of course, if you want to check that. So it's just simply going to be x cubed. Sorry, beg your pardon, x to the power 4. Okay, and then we can just simplify this. Now, to simplify, of course, we need to know what the combination coefficients are, what these evaluate to. You can do those on your calculator using the n-choose-r button. If you want to use Pascal's triangle, it can be quite nice. I'll just write a few of the lines out. So if I start off with it, we have the ones cascading down the left and right hand side, and then if I keep adding a row, I then have to sum the 2 values directly above. So I add those together and I get 2. Okay, and this is the equivalent of doing a plus b to the power 0. So I would just get 1, which is what this is here. They both match. Here I have a plus b to the power 1, which is a plus b. And notice that the 1s correspond to the coefficients here and here. Okay, the 1s in the triangle. And when I square it, I would have a squared plus 2ab plus b squared. So again, the 1, the 2, and the 1 correspond to the coefficients. So that's how it works. So if I just carry on with that, I'll put another row. So 1, and then I'm going to add these 2 together. So that gives me 3. I add these 2 together, I get 3, and then another 1. And then just a bit more room. Okay, so I've got 1, and then if I add those 2, I get 4. So that's going to be 4, choose 1. Then I add these 2 together, so I get 6. That's 4, choose 2. Then these, that's 4, choose 3. And then 4, choose 4, which we don't write in, is, of course, 1. So those are my coefficients. Now, just to finish this off, let's write the whole thing out. It's a nice method, Pascal's triangle. Not very practical if you have 1 plus x to the power 20, but there you go. So our final expansion is going to be 1 plus 4x try that again. Okay, getting the coefficients in there. So that's 4 choose 1 is 4, and then x to the power 1, plus 4 choose 2, which is 6, x squared, 4 choose 3, which is 4, so that's 4x cubed, and then x to the power 4 at the end. Okay, so that's questions 1 and 2. Now, moving on, let's have a look at question 3 and question 4. So this is, we're going to extend, straight away, we're going to extend what we did last year on the binomial expansion. We're going to look in a bit more detail at the combination coefficients. So I'm just going to need to clear these annotations, clear all my drawings. Yes, okay, good. All right, so question 3a, we have to evaluate 3, choose 1. Experience will tell you the answer is going to be 3 because it's always the second coefficient in on Pascal's triangle from the left, and it matches whatever your n value is. But wouldn't it be interesting just to see if this is the case? And it would be a nice extension if you want to try out what n choose 1 actually is and see if you get n. It's a nice exercise. So let's go back to the definition. Now the definition would tell me that this would be 3 factorial over 1 factorial. So remember, this is your n value here, and this is your r value. And just to remind you of the definition, it's n factorial over r factorial, and then we have n subtract r factorial on the bottom. So I have to find the difference between n and r, so that's going to be 2. And I work out 2 factorial. You may have forgotten what a factorial is, so I'm going to write it out explicitly now. A factorial, so for instance 3, is the number itself multiplied by all the preceding natural numbers. So in other words, it's 3 multiplied by 2 multiplied by 1. Okay? Notice I said natural numbers. Okay, 0 is not included. 1 factorial is just, of course, 1. And then just to make it distinct, 2 factorial is going to be 2 multiplied by 1. All right, and you may have noticed something interesting here. There is a nice property of factorials we'll get into in a minute, but you'll notice that there is some very nice cancellation. So the 2's cancel and the 1's cancel, and quite clearly you can see you're going to get just 3 over 1, which is 3. Okay, so that's that one done. For part B, this is 5, choose 2. So again, we'll put everything into the definition. 5 factorial on top, that's my n. 2 factorial on the bottom, and then the extra term, the difference between the n and the r. Okay, the n is always bigger. So 5 subtract 2, which is 3 factorial. Now then, let's write out the factorials explicitly. So we've got 5 multiplied by 4, 3, 2, and 1 over 2 times 1 for my 2 factorial. And then I have 3 factorial on the bottom again. So this is again is going to create a lot of cancelling. Now notice that we've got the 3, the 2, and the 1 again. They're gone. But I've also got some cancellation here between the 4 and the 2. So I can cancel this down to 2 and this to 1. So what I'm left with is 5 times 2, which is 10, over 1 times 1. So it's going to be 10. All right. And it's worth pointing out, if I just look at some of the definitions of the factorials here, something that's really interesting is that if I take 5 factorial as an example, it's the number 5, but I'm multiplying it by 4 times 3 times 2 times 1. Now, let's just consider that. That would be 5 multiplied by 4 factorial, wouldn't it? Okay. So 5 factorial is 5 multiplied by 4 factorial, okay? Or you could think of it as it could be 5 multiplied by 4 multiplied by 3 factorial. Okay, so the factorials are all built into each other. Now we're going to use this property shortly because we're going to have to do 71 choose 70. And just as a word of warning, if you've tried this on your calculator already, you'll notice that your calculator doesn't like 70 factorial or indeed 71 factorial. In fact, your calculator can only handle up to 69 factorial. And the reason is because 69 factorial is some number multiplied by 10 to the power 98, I think. Now, 70 factorial would take the power 98 basically over the edge. It would make it into over 100, and your calculator can't cope with that. All right, so 71 choose 70 wouldn't be feasible. So we need on your calculator. So we need a better way of doing it. And the definition is really nice if we use the definition. So let's just write it out explicitly. So this is 71. Let's write that again. So that's 71. Still on that. Oops. 71 factorial over 70 factorial. And then the difference between the two is just 1 factorial, okay? Right, now, obviously, I do not want to write out 71 factorial, but we can use that property we discussed just a few minutes ago here. So it's actually 71 multiplied by 70 factorial. Because it's 71 multiplied by 70 times 69, 68, 67, etc. So in other words, 70 factorial. All over 1 factorial is just 1. So we're just left with the 70 factorial. Then we get our cancellation. Isn't this nice? So it all cancels. And we're just left with the 71. And you didn't need to use your calculator. Great. Now, let's have a look at an algebraic version of what we've just done. So we're progressing quickly here. We've got, we've been told in question 4 to use the definition of a combination. Okay, we'll do that. And show that n, choose n subtract 3 is what you have on the right-hand side. Well, the definition's here. So I just have to write down what my n and my r are. Well, this is n. Obviously, n is n. But my r is now n subtract 3. So if I sub everything into the definition, hopefully this expression here will fall out of it. Okay, so we're going to have n factorial on the top in the numerator. We're going to have r factorial, so that's going to be n subtract 3 factorial. So that's my r. And then n subtract r factorial. Now I'm going to be very careful with this. So I've got n subtract r. Now r, remember, is the n subtract 3. So I've got to subtract all of this from n. So I'm putting it in brackets so I make sure I don't make a mistake here. And I'll just make my fraction a bit longer. And that's a factorial. All right. Let's just tidy up the denominator. So this is going to be n factorial over n minus 3 factorial. And then if I look at this, well, we've got n subtract n. So they're going to cancel. And then I've also got a double negative. I've got the negative here and the negative here, which means I'm just going to be left with 3 factorial on the bottom. Okay, I hope you can all see that. Okay, if you're not convinced, just write it out at one side. Okay, expand the bracket. So that's n subtract n plus 3. And then these two cancel out, so you're just left with the 3. All right, now we've got the 3 factorial. Now that's probably where the 6 has come from. How do we get the n minus 1 and n minus 2? Well, again, we go back to the definition, don't we, of what a factorial is. So it is in fact n. Now I'll write it out. I'll write out the the whole thing explicitly. Let's give a bit more room here. N factorial, remember, is going to be n, and then we multiply it by all the preceding natural numbers. So there must be n minus 1 coming next, n minus 2, n minus 3. We don't know what n is, of course, like n minus 4, and so on, until we get to 1. That's what n factorial is. And I'm dividing n factorial by n minus 3 factorial, and then also 6, which is what 3 factorial is. Now, remember what I said earlier about how factorials are built into each other. If we look at the numerator, all this here is simply n minus 3 factorial. Okay? Because it's n minus 3, n minus 4, and so on until you get down to 1. So I can replace all that with n minus 3 factorial. Okay? This part I've just shaded in here. Okay? So let's do that. Now you'll see the nice cancellation now. So we get n minus 1, n minus 2, and then the rest I can call n minus 3 factorial. What a bonus. All over n minus 3 factorial times 6. And we can show that there's this really nice cancellation. This is all going to cancel, and we're left with our result. So just one more step now. Okay. So it just demands some knowledge of factorials and their properties, really, to do this. And when we get onto the lesson, we'll be using these kind of results to create a new binomial expansion. Okay, thank you very much. And we'll move on to the worked examples and the ideas momentarily. In year 1, you were introduced to this binomial expansion, which we can see here. And like I said, this is given to you in the formula booklet, so you don't need to worry about remembering the definition, but you do need to be confident in using it. And what I'd like you to do first is to make some substitutions. So rather than using this rather complex looking a plus b to the power n, what we're going to do is we're going to substitute a for or number 1, so a equals 1, and then b is going to be x. So could you just pause the video, please, and substitute in a equals 1 and b equals x, and then write your expansion in the space provided. We'll talk about this in a second. Now you've done that, let's have a look what you should have got. And you might have been able to simplify this a little bit. So if a equals 1 and b equals x, then obviously I get 1 plus x to the power n on the left-hand side, but a closer inspection on the right-hand side, I'm going to have 1 to the power n. Okay, we don't know what n is, of course. Add n choose 1, 1 to the power n subtract 1, and then my x term comes in. So then I'm going to get x to the power 1. And remember, I made a comment in the warm-up that the powers, which we can see here, the n subtract 1 and the 1, they should always sum to the power in your combination coefficient. So in this case, n. So n subtract 1, add 1 gives you n. And it should be the case for every single term. Right, let's continue. So then we're going to have n choose 2, 1 to the power n minus 2, and then we have x to the power 2. Okay, we'll do a few more. Plus n choose 3, 1 to the power n subtract 3, and then x to the power 3. And we don't really know when to stop, do we? We have this generic term given in the definition here. So let's do the generic term. So we'll put plus dot dot dot, and then we're going to add n choose r, and then we're going to have obviously 1 to the power n subtract r, and then x to the power r, like that. And then the final term, we'll just put some more continuation dots here because, again, we don't know what n is, so we have to just account for the fact that this could go on for a long time. And then we're going to have finally x to the power n as our final term. So it still looks pretty complicated. Now, is there anything we can do with this? Let's have a closer look. Well, I've got 1 to the power n here, 1 to the power n subtract 1, 1 to the power n subtract 2, and so on and so on. Now, 1 to the power anything is always going to be 1. 1 times itself is not going to change. So we can simplify this expression immediately. Now, if I do that and just remove those 1 to the power n's and n subtract 1, etc., I'm going to be left with 1 add n choose 1 x add n choose 2 x squared add n choose 3 x cubed. So we can see clearly we've got a much more simple pattern. Okay, it makes a lot more sense. Using a as 1 has made this a whole lot more simpler. Let's carry on. So add, and then we have n choose r. So this just highlights the pattern, doesn't it? X to the power r. So the number on the bottom simply match of the combination coefficient simply matches the power that you have. So the r. Oops, shouldn't have done that. Just redo that eraser. Okay, so that should be there. I meant to use a highlight of that one. So what I was saying was that the number on the bottom, whatever that value is, it is reflected in the power of x, is what I wanted to say. And the final term, so we're going to add some more stuff and then add x to the power n. Now we've made quite a prolific step there. We made a serious simplification of the binomial expansion from last year. Now the question is, can we make this even better, even more simplistic? Well, we probably can. Now, what we need to work on here are these combination coefficients. Is there a simpler way of writing n choose 1, n choose 2, n choose 3, n choose r, and so on and so on? Well, we're going to have a look at 3 cases of this. Now, we're going to have a look at the n choose 1, 2, and 3, and then hopefully we can see a pattern emerging. So let's do that. So for n choose 1, well, we did this earlier. I'm going to write it out explicitly because we saw that whatever n is, if it's n choose 1, you just get the value of n back. But let's just confirm this. So using the definition, which is provided here, I'm just going to put this in a box. We're going to refer to this now, use this definition. We're going to try and show that n choose 1 is in fact n. Now, what you might want to do now is just pause the video and try it yourself before I actually write this out. So feel free to do that. Okay, so let's write this out. So it's n factorial over r factorial. So remember, r is the number on the bottom, so that's 1 factorial. And then n subtract 1 factorial. Let's do a bit of tidying up. Now remember the definition of n factorial. It's n multiplied by n subtract 1, n subtract 2, etc., etc., multiplied by 2, multiplied by 1. So without going through all that working out that we did in the warm-up, again, I hope you're convinced now that this is going to be n multiplied by n subtract 1 factorial in the numerator. That's the same as n factorial, okay? And then in the denominator, we also have n subtract 1 factorial, because the 1 factorial is, of course, just 1. And then we get the really nice cancellation now, okay, with the n minus 1 factorials. And we are left with n, which is what we suspected all along, okay? So n choose 1 is just n. Great news. So that means I can simplify the first two terms of my binomial expansion straight away, because I know this is just going to be 1 plus nx. Okay, so let's see what happens further along our binomial expansion. So n choose 2. Let's apply the definition again. Again, if you want to pause the video and try it, please do. So this is n factorial over 2 factorial multiplying n subtract 2 factorial. Now, again, we're going to use the really nice inbuilt definition of a factorial. I've got n subtract 2 factorial on the bottom of this fraction right here. Now, I'd love that to cancel out. Well, I can show that this will cancel if I write the numerator very carefully. So the definition of a factorial again, and if you like, I'm just going to jot it down over here on the right hand side. Remember what it means. It's n minus 1, n minus 2, n minus 3. I'll stop there, and then all the way down to 2 and 1. Really important. So in other words, n subtract 2 factorial is built in to n factorial. Okay? It's right here. It's staring at us. This is n subtract 2 factorial here. Okay? So I can rewrite n factorial with n minus 2 factorial in it. So let's do that. So it's going to be n, oops. I found the undo button, that's good. n minus 1. And then I can write n minus 2 factorial, because we've seen it here. It's here. That's what n minus 2 factorial is. Sorry if you think I'm over-egging this. I just want it to be really clear. And then 2 factorial on the bottom is just 2. And then I have n subtract 2 factorial on the bottom. That was the bell, by the way. Hope, in case you heard that noise. And we get the nice cancellation. The n minus 2 factorials cancel. And I'm going to be left with a very nice expression here. It's going to be n subtract 1 all over 2. Now, what I'm going to do here is I'm actually going to leave this as 2 factorial. Okay, so I'm going to keep that as 2 factorial there. I know it's the same as 2, but you might see why in a second. So that's what n choose 2 is equal to. Again, if you haven't paused the video yet while we're doing this, try n choose 3 and using the definition here and see what you get. All right, let's have a look at this. So writing it all out again. So we're going to have n factorial over 3 factorial this time. And then the difference between the two, n subtract 3 factorial. And the great news is we can simplify the numerator and write it with n minus 3 factorial built into it. Okay? Again, I'll just remind you. n subtract 3 factorial is this, which means I've got n subtract 1, n subtract 2 as coefficients of n minus 3 factorial. I hope that's okay. So let's write this out. So n factorial is, of course, n minus 1, n minus 2, and then on the end is n subtract 3 factorial. And that's all over 3 factorial and n subtract 3 factorial. And I think the pattern's starting to emerge now, isn't it? So we get this lovely cancellation, n minus 3 factorials go. So there's no factorials at all. So this is n subtract 1, n subtract 2, all over 3 factorial. Now, it would be a nice exercise. Let's have a look at the pattern, what we've got here. Some interesting things going on. We have n choose 2, and we get n minus 1 over 2 factorial. N choose 3, and we get n subtract 1, n subtract 2 over 3 factorial. So can we predict what's going to happen for, let's say, n choose 4? Well, jot down what you think will happen. Okay, I'll pause the video, try it. I'm going to jot it down in a moment. So n choose 4, without doing any work whatsoever, you could verify this using the definition if you like, but it's going to be n subtract 1, n subtract 2, okay, and then an extra term, n subtract 3, because the n subtract 4 factorial will cancel, and that's all going to be over 4 factorial without doing any work whatsoever, because the pattern will continue. So this is quite a powerful result. Now this means we can rewrite our binomial definition, provided, and this is very important that we do acknowledge this, provided we use 1 as our coefficient and positive x, I beg your pardon, 1 as our a and positive x as our b, we now have a really, really nice way of representing the binomial expansion without combinations and without factorials. So let's add our new definition, or our new expansion. So our new expansion says that 1 plus x to the power n is simply just putting everything together that we've just discovered. 1 plus nx plus n multiplied by n subtract 1 over 2 factorial x squared plus n multiplied by n subtract 1 n subtract 2 over 3 factorial x cubed plus more terms. I'm going to leave it like that. When we can see the pattern continuing, but it's not quite clear how this will end, this expansion. But the pattern is pretty clear. What we can do, I wouldn't say this is strictly a new definition. I think what we need to do is test this. So we're going to test this in step 3. And we're going to test it on 2 expansions that we do know the answer to already. So we want to see if our new expansion here can perform the same job as the original definition. Well, let's have a look. If you want to try this, please pause the video and have a go. And I want to stress that you're not going to just expand 1 plus x all squared. I mean, you'll know that the answer is, of course, this, but I want you to use our new expansion, okay, here. Just done that. I meant to highlight that, sorry. I want you to use this. Okay, so please pause the video and have a go. Right. Now let's have a look at this using our new result. So clearly in this case, n equals 2. And I've jotted down the answer in blue, just underneath 1 plus x all squared. Now let's see if this works. So 1 plus x all squared. So that's going to equal 1 plus nx, that's 1 plus 2x. So we can see here the first two terms check out. So we're expecting an x squared, aren't we? Now, if we use the definition, we're going to have n, which is 2, multiplied by n subtract 1 over 2 factorial. And that's the coefficient of x squared. Yes. And then we're going to have to add the next term. So that's going to be n multiplied by n subtract 1 multiplied by n subtract 2 over 3 factorial. And this is the coefficient of x cubed. Okay. And there might be more to come. So I'll just put plus ... here. Now, let's just have a close look. The first two terms are correct. And if we just draw attention to this third term here, particularly the coefficient, just want to evaluate this. 2 multiplied by 2 subtract 1. Well, obviously 2 subtract 1 is just 1. So that's just 1, isn't it? And 2 factorial is just 2. So straight away, we can see this is going to be 1 add 2x plus 2 over 2, which is 1, so plus x squared. So it looks promising, doesn't it? But I don't really want any more terms. There shouldn't be an x cubed term. There certainly shouldn't be an x to the 4 term, and there shouldn't be anything else coming. Is this the case? Ask yourself that question. Well, let's have a close look at this coefficient here. So there shouldn't be an x cubed term. Now, if you look carefully, we have 2 multiplied by 2 subtract 1. That's just 1. Just make that into... So 2 subtract 1 is just 1. Now, if you look here, 2 subtract 2 is 0. That's the key, isn't it? This is just going to knock out the whole of the term. So 2 subtract 2 is 0. That means there is no x cubed term at all. And consequently, the next term after this, so if I continued with x to the power 4 and so on, this n subtract 2 term would feature in all the subsequent terms if you carry on the pattern. So that means you cannot have x cubed, x to the power 4, or any other term in an expansion with n equals 2. So yes, this seems to check out. All right, now if you haven't tried part B, please pause the video and try it now you've seen an example. If you have, we'll go through it now. But if you haven't, just please pause the video. So in this situation, we have n equals 3. So let's test our expansion for n equals 3. Great. So straight away, we know that it's going to be 1 plus 3x. And for the next term, of course, we have n. So this time n is 3 multiplied by 3 subtract 1 over 2 factorial. And that's, of course, the coefficient of x squared. Then we have 3 multiplied by 3 subtract 1 multiplied by 3 subtract 2 over 3 factorial. This is the coefficient of x cubed, and plus some other terms, perhaps. All right, let's have a close look at this. Well, the first two terms check out. If we just quickly do 1 plus x to the power 3, I'll do it over here. Using Pascal's triangle or the binomial expansion, you'll recall it's 1 add 3x squared, add x cubed. You can check that yourself if you want. So that's what we're expecting to get. Now let's have a closer look at these coefficients. So here, the x squared coefficient, we should be getting 3, shouldn't we? Let's just check that. So 3 subtract 1 is, of course, 2. So we have 3 times 2, which is 6, over 2 factorial, which is 2. So yes, of course, we do get 3. So we've got 1 plus 3x plus 3x squared. Seems to work nicely. And then in the x cubed coefficient, let's have a look at this one. We have got 3 multiplied by 3 subtract 1, which is, of course, just 2 again. 3 subtract 2, which is, of course, 1. So we have 3 multiplied by 2, multiplied by 1, which is 6, over 3 factorial, which is 6. 6 over 6 cancels to 1, plus x cubed. So, yes, it does indeed work. And similar to the previous example, part A, if we continued the pattern, remember we would have n subtract 1, n subtract 2, n subtract 3 over 4 factorial. That would be the coefficient of the x to the power 4 term. And notice what would happen here. If we have n equals 3, this would be 0, which means that you cannot have powers 4, 5, and so on and so on. It simply will not work. So it seems to work. It seems to work for normal natural number powers of x. Now, what we have done in rewriting our expansion is we've removed the n choose r. Now, I've put a bit of blurb here about this. We've expunged the n choose r. We don't need it anymore. And why is this useful? Well, n choose r is great on your calculator if you're dealing with natural numbers. But if you try to do something such as -5 choose 2 on your calculator, and you can try it, you're going to run into problems because we don't have and -5 is not a natural number. Okay, that has no solution whatsoever. There's no value for -5 choose 2. And the reason why is because from the definition, the combination, it's using factorials. It's the number of ways to choose a sample of r elements from a set of n distinct objects. So you can't have -5 distinct objects. Okay, it doesn't make sense. So in year 1 and in old money, the number at the top would have to be a natural number. But we've dispensed with the combination coefficient. We've got n's, n-1s, n-2s. There's no reason. So if I just go back up to this definition here, there is absolutely no reason why we can't substitute in any real number for any of these, really, because we're not restricted by the combination anymore. So this is what we're going to explore, and we're going to see, does this generate sensible answers, and is it valid? Our first works example, we're going to use our generalized binomial expansion, and we're going to use, which is rather exciting this time, we're going to use a negative power for our n. And this will open up our expansion into a whole new realm of possibilities. Well, hopefully it will. Let's see what happens. So this is our first step over the threshold, really. So I want to find the first 4 terms in the expansion of 1 over 1 plus x. So notice we have the 1 plus x. First of all, that's the format that we've been working on. We've been working on 1 plus x to any power. So the first thing we need to do is find out what power of n is this 1 plus x being raised to. And this is going back to your laws of indices, isn't it? So we first need to spot that this is, of course, 1 plus x to the power -1. Yeah, they mean the same thing. So now we can apply our expansion. You might just want to write it out if it's not in front of you, the expansion. I won't do that, but just make sure you've got it handy. The only value we need to sub in, of course, is n as -1. So I'll just jot that down. So n equals -1. And we can carry out the expansion. So writing it out fully, we're going to have 1 plus x to the power -1 is equal to, now the first term is always 1, plus, now it's going to be -1, which is our n, multiplying x. And when I do this, I'm going to use brackets when I'm carrying out the multiplications. I recommend you do the same thing. It will limit the number of errors you're going to make with signs, because signs are going to cause a few difficulties as we go through this process. So that's 1 plus nx, and then using our definition, we have n multiplied by n subtract 1 over 2 factorial, and that is the coefficient of x squared. So we have 3 terms so far, and we need one more term, plus n multiplied by n subtract 1 multiplied by n subtract 2 all over 3 factorial, and this is the coefficient of x cubed. And we'll just acknowledge that there's more to come here. Just as a note, if I'm using the I want the highlighter, sorry. If I'm using the plus ... over there, it's reasonable that I use an equal sign here, but I'll get on to that a bit more in a minute. But what I'm saying is that those two pieces of notation, the equals and the plus ... go together. All right, they meet, they're part of the same idea, but I'll talk more about that later. So the next step, we just need to simplify this a little bit. So this is going to equal 1, and then we've got subtract x, and we're going to have plus -1 multiplied by -2 over 2 factorial, which is 2. And notice I'm putting in another step here. I'm not trying to do too much in one go. There's no need to do that. You're just asking for trouble. So -1 multiplied by -2 multiplied by, now it's going to be -1 subtract 2, so that's -3 over 3 factorial, which is of course 6, and that's going to be x cubed plus some more terms. And our final step, we can tidy this up a bit more. So we have 1 subtract x, and then we're going to add -2 multiplied by -1, which is of course 2 over 2, which is just going to be 1, so that's x squared. And then we have 3 negatives here. Just bear that in mind. 3 negatives, 1, 2, 3. So an odd number of negatives means this is going to be a negative term. So before I do any work, I can put in a negative sign here. And then we have 3 multiplied by 2 multiplied by 1, which is of course 6, divided by 6, which is of course 1. And I have x cubed plus some other stuff. I've been asked the question a few times. If you've got negatives here, or if these were all negative, do you still put a plus ... Yes, you do, because you're adding negative terms. That's absolutely fine. So if you're showing that there's a continuation, you're well within your rights to just put plus ... all the time. Another thing to notice is, if you want to make sure you've done this correctly, there should be a pattern in your expansion. And what I mean is, it could be the first term is positive. Oops, just undo that, sorry. First term is positive here. The second term is negative. The third term is positive, and then the fourth term is negative. So it's going plus minus plus minus plus minus. So there's an alternating pattern. or they might all be plus, or they might all be minus, but there should be some kind of pattern with the signs. Okay, that's a good rule of thumb to tell you that you've done this correctly. So it looks like we've done our expansion. Now then, what this means, of course, if you just go back to the original question, is that all of this is equal to 1 subtract x, add x squared, subtract x cubed, plus some more values. Now, at face value, if you go back to the 1 over 1 plus x, it looks unusual. It doesn't look like you're going to get the same values, and depending on what x is, of course, I think this is going to be a false result at first glance. I can't see any way you could get 1 over 1 plus x to equal this kind of expansion here, where you're continually adding new terms. But that's what we're going to explore next. Is this a reasonable result? So next, what we want to do is check whether this result is actually feasible or not. Now, what I've done here is I've said, well, we acknowledged earlier you could have a straight equals if you acknowledge that there is more to come. Now, and in this situation, I put a squiggly equals, and if you remember, that means approximately. So are these two expressions approximately the same? Because we have a rational expression there and a polynomial, and they look like they're going to yield totally different answers. Now, what I would like you to do is just pause the video and on your calculator or otherwise, evaluate these two columns. And you're going to sub in x equals 4 into the first expression here, 1 over 1 plus x. Okay, so we'll do this one together just to get you started if you like. So if I put 4 in, that's of course going to be 1 over 5, which is 0.2. Okay, and then you're going to substitute x equals 4 into this expression here. And when you evaluate that one, you'll get negative 51. So if you could repeat that process for each other row, and then we'll have a look at our findings. All right, so now you've done that. Just we'll compare notes and make sure that you're happy with this. So if I substitute in 1, I will get 0.5, 1 over 2, of course. And interestingly, on the right hand side, I would actually get 1 subtract 1 plus 1 subtract 1. So alternating signs of 1, and if we add all that together, we of course get 0. And if I'd have stopped my expansion one term earlier, if I'd have completely ignored this term, I would have got a completely different answer, which is also interesting. So the answer, depending on how many terms you have, is going to of course be 1 or 0. It's like a binary answer. For x equals 0.5, if you substitute that, I'll do it in decimal form, you're going to get 2/3, which is of course 0.6 recurring. I'll do it to 3 decimal places, so 0.667. But yeah, that's 2/3. And then if you evaluate it on the right hand side, we get 0.625. which look reasonably similar, don't they? It's not a million miles away. And then for x equals 0.1, if you substitute that in, we get 0.909, and that's a repeating pattern. So that's the answer to 3 decimal places, of course, or you could put the dots there. It doesn't really matter. Okay, it's just roughly what the values are that we're interested in. And what's interesting is if you do the same thing on the right hand side, you get precisely 0.909 as a terminating decimal. That's interesting. If we put in x equals 0, we get 1, of course, on the left. And we also get 1 on the right. We get a match. They are precisely the same. That's also interesting. X equals negative 0.5. Well, that's going to be 1 over a half, which is, of course, 2. And then if you substitute negative a half into the right-hand side, we get 1.875. Not too far out. Okay, they're reasonable answers. I think that seems to be about the same. And I'm sure if I added more and more terms, we would get the same or an even better approximation. But we'll talk about that a bit more in a minute. If I put negative 1 into the denominator on the left-hand side, of course, I'm going to get 0. So this is undefined. It doesn't have an answer, essentially. Okay, it's an asymptote. And then if we put negative 1 on the right-hand side, we get something completely different. We would actually get 1 plus 1 because obviously you're subtracting a negative, plus 1 plus 1, which is, of course, 4. Wildly different conclusions there. And then for the last row, we would get negative 1 for the left, and we would actually get 1 plus 2 plus 4 plus 8. Just getting bigger and bigger, which gives us 15 in this instance. And of course, that if I added more terms, it would just get bigger and bigger. Now, what is this telling us? Well, I'm hoping, or if this is to go anywhere, this whole idea, if these are roughly the same, then I can't, in good conscience, put in x equals 4 here, okay? Because the answers are vastly different. I mean, they're so different. We couldn't possibly justify that, okay? But x equals 4, definitely not. If I put in x equals 1, this is a strange result, isn't it? I get 0, but I could have easily have gotten 1. And you could argue that they are reasonably close, but I'm not sure. I think the jury's out on that one. I'm going to put a question mark next to this for now. I don't think we can conclusively say that that's a good approximation, because we are just going to alternate between 0 and 1. For x equals 0.5, now this is reasonably close. I think this is a reasonable estimate, and we can test this by adding more terms if we like. So I'm quite happy with that one. I think this is a reasonably good estimate. Okay, and even better is when I sub in x equals 0.1, I get almost the same answer. They're very close. And when I get to 0, I get a perfect answer. Okay, so, but is that just an anomaly? Standout result? Well, we've got 3 in a row there. And then if I put in x equals negative 0.5, I'm going to get 2, and then my approximation on the right-hand side was 1.87, which is pretty close, and I think that's a good result. So I'm gonna say, yeah, that's a good result. And then we get something undefined and 4. I think we can dispense with this, and then we get something wildly different again. So what appears to be happening is we seem to have this area of convergence, if you like, that where they seem to be the same. And if I ignore that, I think anything between those 4 results is a good approximation. The question is why? Well, if we look at the right-hand approximation, if I just write out what we're actually doing here, we've got 1 subtract 0.5 plus 0.5 squared subtract 0.5 cubed, and plus lots more terms. Now, if we consider what's happening here, we talked about this in an earlier example in the warm-up. Was it sometimes true, always true, or never true? When you square a number, you always get a number which is greater than the original number. Well, this was a case where it's not true. If I square 0.5, I get 0.25. And if I cube 0.5, I get 0.625. So what we're doing is we're adding smaller and smaller values every single time. Oh, I just realized that's wrong. Sorry. It's not. Let me just get rid of that. Not thinking. That should be 125. I apologize. That makes more sense now. So I'm subtracting 0.125. Here I'm adding 0.25. But the point is, I'm adding and subtracting smaller and smaller amounts. So this is what we call a convergent series. This converges. Same way, if I look at the expansion for 0.1, I'm going to be doing 1 subtract 0.1 plus 0.1 squared subtract 0.1 cubed. Each of these values is getting smaller and smaller and smaller. It's converging. And when I put in 0, the whole thing just terminates and I just get 1. So it seems to hinge on the fact that when I'm adding or subtracting smaller and smaller amounts, when I'm squaring or cubing or raising it to a higher power, that's when our approximation seems to be valid. So what we need to do is we need to broaden our definition now. We need to say, well, our expansions are valid, but only for a very limited number of values. And you can probably guess from what we've talked about that these values are valid for a reason, okay? Because they're going to produce, when we raise them to certain powers, they are going to get smaller and smaller and smaller. The other values that you substituted in, such as x equals 4 and x equals -1 and -2, those are just going to add larger and larger values or subtract larger and larger values. They're going to diverge. So we want values that converge, and the only way to produce convergence is to use fractions between 0 and 1 or between -1 and 0. Just so we have a deeper understanding of what's actually at play here when we try to approximate 1/1 plus x using an expansion, I just want to remind you what actually is going on here. So what I've got plotted here is the graph of 1/1 plus x. You can see there's two asymptotes, one at y equals 0 and one at x equals -1. I'm not too interested in those at this stage, but you can see if I disable that, so the graph f is the red curve. So this is the left-hand side, if you like, of the equation. So 1 over, just get rid of that. Sorry about this. Getting used to these pens. So 1 over 1 plus x. And we know that is roughly equal to 1 subtract x plus x squared minus x cubed, and so on and so on. So what I've done, I'm going to build up the approximation. So let's suppose, for instance, we just looked at the first two terms of the expansion. We only did the 1 plus nb part of the expansion, if you like. Well, if we did that, we will get this graph here, 1 subtract x. Okay, so that's the straight line 1 subtract x. And notice it's tangent to our curve 1/1 plus x. So as an approximation, if we look carefully, it's pretty good around this kind of range. All right, you can see it's the graphs are fairly close, but anything outside of that range, it isn't particularly accurate. Now, if I add another term, which I'll do here, so this is going to be 1 subtract x plus x squared. That's the quadratic expansion. Now, might be a good idea to zoom in a little bit here, which I will do. I'll just clear our annotations. Now, if I zoom in, the quadratic is the black curve. Now, we can see how this black curve approximates the original curve 1 over 1 plus x a lot better. Okay, and then the range of validity, as we know, is between -1 here. Oh, just realized I'm not writing anything. No, sorry. I'm just a bit clunky with this still. All right, so range of validity between -1 and 1. So once again, anything outside that range isn't valid. And as you can see, the quadratic is pretty close to the curve, but not quite. Okay, but it might be a better approximation than the straight line. Now, if I add another term, so let's put the cubic graph on there, like so. Now we get an even better approximation. So we're getting closer and closer. I'm doing it again. We're getting closer and closer to the real curve, if you like, if you want to put it that way. So we're now moved very, very close indeed. And down here as well. All right, so that looks like a good approximation. And once again, within our limits, it's a pretty good approximation. Now I can keep doing this. If I add another curve, sorry, I beg your pardon, another term, I get the quartic approximation. And once again, this is giving us a really good approximation within a certain range. Okay, so we've gone from the straight line to this value here, and we are a lot closer to the curve now. And the more I add, the more accurate the approximation will be. So I just wanted you to see that, because it just gives you a visual representation of what you're actually doing when you're adding the terms to the expansion. So if I just zoom out, remember the original curve was the red is the red curve 1 over 1 plus x, and each time I add a term, yes, the curves flip from 1 to 1 to 1 to many because of the positive, not positive, but because of the odd and even powers of x. But generally speaking, the curves seem to be converging closer and closer to the red curve. So to complete our definition, we'll place our restriction on the values of x we're allowed to use. So our values of x can only be, and this is really important, that you're only allowed to substitute in values between -1 and 1. Otherwise, you will get divergent series, which we do not want to get. So to complete our definition, we need to add this restriction. So our full definition is as follows. So 1 plus x to the power n is everything we've discussed already, okay, with the added restriction on x, okay? And what's really nice is our n can be any real number, all right? So it doesn't restrict us in any way. As long as we're careful using only these values of x, we're allowed to substitute in any real power for n. So for example, if you wanted to, you could expand 1 plus x to the power root 2. Okay, it would be a bit messy, but you could do it. Now then, before we do our worked example, our next worked example, I want to talk about the general form which I'm going to use from now on. And I strongly recommend you use this. It's slightly different from what's given in the formula book. And the only difference is that I'm using the letter capital B here. Okay, now I'm doing that instead of using X. All right, so if you look this up in the formula booklet, you will see an X wherever you see this B. The reason I use the B is because, remember, the original expansion from year one, it was the form a plus b to the power n. So I've just retained that letter B. But also, as you'll see in the first example we're going to do here, you're going to be substituting in a value for B. Well, not a value, but you're going to be substituting in some amount of X for B. Now, if you use X as in a single X, like what's given in the definition, you'll be substituting in something like X equals 4X, as if we sort of refer to the first example we're going to do in a minute, and that becomes confusing. You don't want to be substituting in X equals 4X or X equals 3X. Just becomes a little bit dubious. So I want to be clear that our substitution is going to not be ambiguous. All right, so I want to use letter B. I hope that's okay. So in the first example here, we're asked to expand 1 over 1 plus 4x to the power 2. So it's in that form. It's the 1 plus b form. I'm going to write down what my b is straight away. So in this example, my b is equal to 4x, and this saves me writing x equals 4x, which is just very poor notation. We also need to know what our n is. So remember, if we go back to the definition that I've put here, n is featured all the way along. Okay, so we're going to need to substitute in our n. Now, to get our n, of course, we need to we need to find out what power we're raising our 1 plus 4x to. So it's clearly going to be 1 plus 4x to the power negative 2. Okay, so that gives us our n. So our n is going to equal negative 2. So there are just two substitutions to make. And once you've established your n and your b, you're free to substitute everything in. Another thing we also need to keep an eye on is how many terms. So we're only interested in up to the x cubed term. Okay, and we also need the range of validity, all right, which is that property we've just been looking at. So let's get straight into it. All right, so let's write down our expansion. So 1 plus 4x to the power negative 2 is going to equal, well, 1 is always the first term, plus nb, and I've put over 1 factorial in the definition here, which is strictly the correct way to do it. I mean, you could put 1 over 0 factorial if you liked as well. So n times b, so I have to multiply these two things together. So it's going to be negative 2 multiplying 4x. Okay, I won't bother with the 1 factorial on the bottom. Plus negative 2. Now it's n subtract 1, so that's negative 2 subtract 1 over 2 factorial. And this is where I need to be careful. My b is being squared here. Okay, remember b is 4x. So whatever my b is needs to be squared. I'm going to put it in red. B squared. 4x all squared. Please be careful with that. Very common error in the binomial expansion. So that's going to be our x squared term. Let's add some more, or let's add one more. So it's going to be n minus 1, n minus 2 over 3 factorial. Notice it's not given there, but because we've dealt with this a few times now, we can see the pattern. and then our b is going to be cubed. So this is going to be 4x all cubed. And then I will just acknowledge that there might be more to come. Okay, if you wanted to use the approximation symbol instead, you can. So remember I said earlier that the equals and the plus dot 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 are part of the same definition. They're the same notation, if you like. You could use the wiggly equal sign if you wanted to, like this. Okay, but what you would have to do is you wouldn't use the plus dot dot dot, because you're saying the left hand side is roughly the same as the right hand side, so you wouldn't have the exactitude of having plus more stuff to come. I hope that makes sense. Okay, let's carry on with the expansion. We just need to tidy up our terms, don't we? So maybe a couple more steps here. So this is going to equal 1 subtract 8x. Usually on the exam, you would get a mark for getting these first two terms done correctly, as well as a method mark for writing out the binomial expansion correctly too. So that's going to be -2 multiplied by -3 over 2. And then 4x squared, well, that's going to be, so I'm going to multiply that by 16x squared. All right. Just want to highlight that. Okay, 4x squared becomes 16x squared. 4x all squared becomes 16x squared. Let's continue. Plus -2 multiplied by -3 multiplied by -4, this time over 6. And then I have 4x all cubed. Now 4 cubed is of course 64. So it's going to be 64x cubed plus some more stuff. Right, let's see if we've got any cancellation. Well, yes, we do. Okay, the 2 and the 2 will go, and we have 2 negatives, so that's going to be positive. And then here, we're going to have 2 times 3 is 6, which will cancel with the 6, so all that goes. So I think we're ready to write down our answer now. If you're not confident with that, of course, just use your calculator. So this is going to be 1 subtract 8x. We have a positive term here, negative and negative is positive. And then we have 3 times 16, so that's going to be plus 48 x squared. And then in the final term, we have -4 multiplied by 64, which is essentially 4 cubed. Sorry, I beg your pardon, 4 to the power 4. So that's going to be -256 x cubed plus some more terms. Now, again, let's just recap, or let's just go over our answer. Does it make sense? Well, it looks like we have the alternating pattern. So we have plus that we don't write in. Okay, plus, minus, plus, minus, plus, minus. Okay, so that there's minus there, minus there. So the next term would obviously be a plus. Okay, that's the first thing. So that suggests it's the correct approach. So there's our expansion. Now we've done the first bit. So we've expanded it up to and including the x cubed term. Now we just have to find the range of validity. Well, the range of validity, which I'll write down at the bottom. I hope you have enough room. We go back to the definition. And it just means which values of x are we allowed to substitute into this. It's not simply just anything between -1 and 1. Okay, so if you go back to the definition, remember where I replaced the x from the original definition, it's now replaced with b. So it's wherever your b is between, whatever your b is, the b value has to be between -1 and 1. So in my case, or in your case as well, it's got to be all the 4x values between -1 and 1. Now, to get the x values, we're going to need to divide our inequality by 4. So, i.e., anything from -1/4 up to 1/4. And there is the range of validity. So, if you want to do this quickly, of course, you want to write down the range of validity from scratch. You'll notice, well, in the original question, we had 4x. Yeah, that's your b value. So the reciprocal of that, well, without the x, of course, is going to be your range of validity. So between -1/4 and 1/4. If I was, of course, substituting in 5x, it would be between -1/5 and 1/5. 6x, -1/6 and 1/6. All right, and you get the idea. Our next example, we're going to expand 1 subtract x to the power, well, we'll find out in a second. So it looks like it's the cube root, doesn't it? All right, so I don't want to give it away. Have a think what that power might be and just jot it down. Okay, so what we're expanding to, so it's going to be 1 subtract x to the power 1/3. All right, so this 1/3 here, this is going to be your n. Let's write down what our n and our b are going to be for this question. All right, so n is going to equal 1/3, of course. And b, now let's just have a look what we have here. Remember, the form is 1 plus x, isn't it? So just to make it clear, it would be 1 plus minus x to the power 1/3. So that tells us that our b is going to be -x. Let's write that in. Just be careful, okay? Obviously, if you get that wrong, it's going to have repercussions later. And then we go back to our definition and we sub everything in. This time, we're interested in everything up to the x cubed term. And we also need the range of validity for x as well. So do read the question carefully. You don't want to be doing more work than you need to, or you don't want to be doing less work than you're supposed to. All right, so I'll just box that off. So we have 1 subtract x to the power 1/3 is equal to 1 plus nb. Okay, so I just multiply my n and b together. That's 1/3 multiplying -x. So the first two terms are done. They're always nice. Then we have to be really careful. So it's going to be n multiplied by n subtract 1 all over 2 factorial. Now that's the coefficient. So now I have to square my b. So whatever my b is, I square it. And I'll write it in red. So it's -x all squared for that one. And for the final term that I'm required to write down, so it's going to be 1/3 multiplied by 1/3 subtract 1, 1/3 subtract 2, all over 3 factorial. Okay, and then my b is going to be cubed this time. So that's going to be -x cubed. And I just want to acknowledge that there might be more terms to come here because I've put a straight equal sign, haven't I? Plus dot, dot, dot. All right, so it's just a tidying up exercise now. So we have 1 and then -1/3 x First two terms are always okay. Now, again, don't try and do too much in one go. So I think 2 more steps is enough. A third subtract 1, so that's 1 over 3 subtract 3 over 3, which is negative 2 over 3 over 2 factorial, which is 2, and then it's negative x squared. Now, the negatives will, of course, become positive. Okay, hope that's all right. And then we move on to the third term. So once again, we have a third multiplied by negative 2/3. There's no need to spend time working out a third minus 1 again. We've already done it. And then we have a third subtract 2. So 2 in terms of thirds will be 6 out of 3. So that's 1 subtract 6, which would be negative 5 out of 3. If you're not confident with this, please just use your calculator. Don't try and be a hero. If you're not confident, you can always double check, can't you? And then negative x cubed, well, that's going to be, the negative cubed is of course going to be negative again, so it's going to be negative x cubed like that. All right, I hope that's okay. So that may make the term negative. We'll find out in a minute. So this is going to equal 1 subtract 1/3 x. And let's just multiply the fractions together. So we're going to have negative 2 over 9. All right, and that's going to be all over 2. Sorry about the bell if you heard that. Okay, and then that's going to be x squared. All right. I could put a plus in there. It's obviously going to be negative, isn't it? Next up, we have negative. Let me just show you what I mean. You can't see me waving my hand around. We have a negative, and another negative. So this is going to be a negative term. So I'll put that in first. And then we have 1 multiplied by 2 multiplied by 5. So that's going to be 10, negative 10, over 27. So that's 3 cubed in the denominator. And that's going to be all over 6. All right, and I brought the negative to the front there. So that's going to be x cubed. Plus some more terms. Right, now we can finish off. Now, so again, we have 1 subtract 1/3 x. Now, if I'm halving, so it's 2/9, negative 2/9 divided by 2. Half of 2/9 is, of course, just 1/9. So that's minus 1 over 9 x squared. And then here I have 10 over 27 multiplied by 6. Well, you can get a little bit mixed up when we do fractions divided by fractions or whole numbers. So if you like, if I do 10 over 27 and I'm dividing by 6, multiplied by 1 over 6. Yes? From pre-GCSE. So I can cancel these down. So that's going to be 5. That's going to be 3. So what we essentially have is 5 over 81 for my coefficient there. So that's going to be subtract 5 over 81 x cubed plus some more terms. So that seems to be the expansion. So we've got all the terms we need. We just have to state the range of validity. I'll just box this off here. So the range of validity. You'll get a mark for usually a B1 mark for stating the range of validity. Always worth doing properly. Make sure you understand what you're doing and don't forget don't forget it's part of the definition as well. So this is your b value. Now, remember your b value here is negative x. So if I write it like that, it just looks a bit odd, doesn't it? I've got to multiply the whole inequality by -1. Now, if I do that, of course, I'm going to have a sign switch. That is no longer a true statement, is it? Okay, so what I need to do is switch the inequality around. So when I do that, I'll go back to blue, it's a bit brighter. So if I times everything by -1, I'm going to have 1, and then I have to switch the sign around, x, switch the sign around again, -1, which is exactly the same as this. So it makes no difference, really. Okay, you've just got to acknowledge that when you're dividing by or multiplying by a negative, the inequality sign has to switch around for this reason here. Next up, we have a bit of problem solving. So this time, we're given 1 plus kx to the power -4. So that's what we're expanding. And we're told that we're going to use the definition. We're going to go through the steps, and then hopefully we'll have an equation to solve. So it's nothing to worry about when you see this. It's just a case of, are you confident enough to just go through the steps as you normally would? Remember, when we learn maths like this, the rules do not change for each different scenario. They're always the same. So just have the confidence to just follow through with the steps, and don't worry about the abstraction or the use of like K's or any other letter. Please don't let that put you off. Just go through the steps. So let's write down what our N and our B are in this case. All right, so this is for part A. So my N is obviously going to be -4. Just be aware of that. So remember that this is the B part here. Okay, so just so you're aware of that. Right, let's write out the expansion. All right, so 1 plus kx to the power -4 is of course going to be 1 plus, now it's n times b for my x term. So that's going to be -4 multiplied by kx. And it's the x term that we're actually given the value of. But if I just scan ahead for part B, it will ask us to find the corresponding coefficients of the x squared term. So it would be a good idea just to do another term here so we can use it in part B. So that's going to be n times n minus 1 over 2 factorial, and then it's the b part squared. Okay, and then there will be other terms as well. So let's tie these up. So this is going to equal 1 subtract 4kx. And again, I don't want to do too much at once. That's going to be -4 multiplied by -5 over 2 factorial. And then we're squaring kx. All right, so that's going to be k squared x squared, plus loads of other terms as well. Okay, and then one last step just to tidy this up. So this is going to equal 1 subtract 4kx. And then we have 4 times 5 is 20. The two negatives become positive over 2. So that's going to be plus 10 k squared x squared. All right. I'll just remind you again, the biggest mistake people make when they're doing this is that when they're asked to square the b part, that's why I use the b part, the b substitution, is they have to remember they've got to square everything, okay, including the coefficient. You have to remember this, it's really important. All right, so are we ready to find the value of k? Well, I think so. So we're told that the coefficient of x is 20. Now, the coefficient of x is all this, including the negative sign. All right, it's the amount of x you have. So we can write down an equation now. So this means that negative 4k must be equal to 20. And it's the simplest equation to solve. So therefore, k must equal negative 5. And there we have it. Okay. So that's A finished. Now for part B, we have to find the corresponding coefficient of the x squared term. So for part B, we won't need much space for this. The x squared term, which I will highlight, the coefficient is plus 10k squared. Okay, plus 10k squared. So that plus 10k squared must equal some value, but we know what k is now. So 10k squared equals 10 multiplied by negative 5 all squared, just substituting our k in. Okay, negative 5 squared is of course 25, so it's going to equal 250. There we go. So we've got our coefficient of x squared. And finally, just as a bonus mark, I'll do this over here. We just need to find our range of validity. Okay, so we know k is negative 5 now. So the range of validity if we use the definition, so remember it's anything between -1 and 1 for your b value. The b value is kx. So in other words, -1, and then I'll substitute the b in, so that's going to be negative 5x. And so negative 5x sandwiched between -1 and 1. I'm going to divide through by negative 5, of course. Now that's going to reverse the inequalities as well. So we're going to have 1/5 greater than x, which is greater than -1/5, and just switch everything round. So x must be between those values for this to be true. Okay, and we've finished. So in our final example, we have a rather complicated looking function f of x. Now, we're asked to find the x squared term in the series expansion of f of x. Now, we haven't seen anything quite like this yet. So we'll just go through the idea quite carefully initially. The first thing we need to establish, of course, is what does it mean by the series expansion? Well, we need to remove that square root symbol. All right, so it's the x squared term. Now, let's just rewrite our function. So we know it's 2 plus x, which is our numerator. And we're going to multiply that 2 plus x by the denominator. Now, obviously, it's going to be a negative power. But what is the negative power exactly? So it's 1 plus 5x to what power? Well, it's a square root, isn't it? And if you know anything about square rooting, it's got a fractional power. It's a power of half. So it must be 1 plus 5x to the power negative 1/2. Okay. So let's use the space we've got here and see how we can do this. So I'm just going to rewrite that again. So it's 2 plus x multiplied by 1 plus 5x. I'll just make that power look a bit more actually like a power, to the power negative 1/2. And in fact, I'll erase that top bit. It just looks a bit confusing. Sorry. Okay, it's a bit better. Right, so let's focus on the expansion. So we need to deal with this, and then whatever we get, we obviously need to multiply it by 2 plus x. Well, we can do this all in one step. Well, I don't mean in one step, but we can set an equal sign here and do this properly all the way along. So it's going to be 2 plus x multiplied by whatever we get for the expansion. Now I'm going to use a big square bracket for this while we evaluate our expansion. And because it says in the question that we need to go up to the x squared term, it's a good idea to expand our brackets here also up to the x squared term. Okay, and you'll see why later on. So let's just write down what our n and our b are. So my n is, of course, negative 1/2, and my b is 5x. So this is a real challenge, isn't it? We have a negative fractional power. Sorry, I beg your pardon, 1 plus nb. So negative 1/2 multiplied by 5x. That's the first two terms. We only need one more term, remember. And then we take out b and we have to square it. So I just like to put brackets in just to remind me that I'm squaring it. I'm fully aware that we might get this square. Oh, that's okay. So the next step is we have 2 plus x. Big brackets. 1 over 2x, and then plus negative 1/2 multiplied by, so minus 1/2 minus 1, that's negative 3 over 2. Just be careful with that step, please. Over 2 factorial, which is of course 2, and then that's going to be multiplied by 5x all squared. So in other words, 25x squared. Okay, plus dot dot dot. And I think one more step just to tie that up. So this is going to be 2 plus x multiplying 1, subtract 5 over 2x. We have two negatives multiplied together, so that's going to be 3 over 4. Divide that by 2. That's going to be 3/4. 3/4 of 25 is going to be plus 75 over 8x squared. Just go through that again. So 3/4 divided by 2, that will be 3/8 multiplied by 25, so that would be 75 over 8, plus some more terms. So now we have to expand fully up to the x squared term. Now, what I like to do here is we can do this, no problem. I'm just going to be very careful how I set out my working. I don't want to get muddled up. So I'm going to consider each of these terms in my expansion as a place value. So I'm going to have like constants here, x's here, and x squareds here. Okay, and then obviously there would be x cubes and x to the power 4s. So when I multiply this out, which I'm going to do now, I'm going to start with the 2, and I'm going to multiply everything in here by 2. So that's the first step. So when I do that, so this is going to be my constant. So I'm going to have, oops, undo that. Let's get back to the normal pen. So we're going to have 2. Then 2 lots of this is going to be negative 5x. And then if I multiply 75 over 8 by 2, I'm going to get plus 75 over 4 x squared. Okay, so see how I've got my columns there. Just re-emphasize that. So I've got constants, x's, x squareds, and I've multiplied by 2. My next task, I'm going to multiply by the plus x here. So I'm going to multiply all of this by plus x. Now, if I do that, of course, if I do x multiplied by 1 here, as I do here, that of course is going to give me x. So that needs to go in my x column. Okay. Then I move on to the next term. So it's going to be x multiplying negative 5 over 2. So that's going to be negative 5 over 2 x squared. So that the powers of x just increase. And then I could, in theory, do x multiplied by the 75 over 8 x squared here. But I don't need to do that because that's going to give me a cubic term, an x cubed. And I'm not interested in the x cubed terms. I'm only interested in the x squared terms as stated previously. All right. So now I've done that, I can say, okay, these are my, so I've got my constants here, my x is here, my x squareds here. And what I need to do is just to add up my x squareds. So I need to add up these two terms, and I've got my answer. All right, so let's do that. I hope that's clear, guys. So for part A, just to finish off, the x squared term is going to be 75 over 4 x squared subtract 5 over 2 x squared, which equals 75 over 4 x squared. Now I'm just going to change it into quarters. Subtract 10 over 4 x squared. All right, same denominators now. So that's going to be 65 over 4 x squared. And there we have our answer. Okay, so there's quite a lot of work there. But as long as you're careful and you're consistent, you'll be absolutely fine. Now, I'm just going to box this off over here. We're going to do part B, which is, again, a bonus mark. State the range of values of x for which the expansion is valid. Okay, well, again, you just go back to your B value. So your range of validity right, remember it's between your B value between -1 and 1. So i.e. you're going to sub in. So it's, what is it, 5x into that. Okay, and all I have to do is divide by 5. There's no negatives to worry about here. So this is going to be -1 over 5 x and 1 over 5. Now, just to conclude, we have to have a range of validity because of the expansion. Okay, this expansion here requires a range of validity. Obviously, if you're considering 2 plus x over here, you can put whatever you like into 2 plus x. Yeah, there's no restrictions at all on x, but because we have this expansion here, we have to take only the values of x that are valid for that expansion. Okay, because it's part of the product and it is the most limited part of the product. Okay, so you always take the strictest the strictest restrictions on x in your expansion, because that's the only way. Ooh, there's the bell again. That's the only way you can guarantee that those values of x will work, and then you'll get a sensible answer. Okay, so that concludes the lesson. There is an exercise for you to have a go at. I strongly recommend you complete all the questions in the exercise, and if you have any problems, please contact me.